Welcome viewers to the NPTEL lecture series on the calculus of variations. This is the 19th lecture of the series. Recall that in the last lecture we considered a functional of the type I y equal to integral x 1 to x 2 f of x y prime x dx, subject to the conditions that the functional to y 2. So, we have the situation here that the point A, which is having coordinates x 1 y 1, is having a central feed here at this point. So, we have the extremals going like this, and we assume that the extremals are given as y equal to y of x c. So, this is the family of extremals forming. So, the one parameter family y equal to y of x c, where c is the parameter, forms a central extremal field at the point A x 1 y 1, and the extremal y equal to y x c 0 passing through A x 1 y 1 and B x 2 y 2 is an interior extremal So, that means here this extremal, which is A B x 2 y 2. So, this is the extremal here, which is having the equation y equal to y x c 0. So, for the fixed value of c equal to c 0, we have this extremal passing through these 2 points A and B, and this extremal is not on the boundary. So, it is an interior extremal, and so here this family of extremals like this forms a central field at the point A. So, we assume that the Jacobi condition is satisfied, that is, the solution u of the Jacobi equation Jacobi's equation given by f y y minus d by dx of f y y prime times u minus d by dx of f y prime equal to 0 vanishes only at the point A x 1 y 1 and only at x 1 y 1 on the interval x 1 to x 2 close. So, that means at the point B it does not vanish, and so we have like the situation here, that if we consider C discriminant curve, and so we have, in addition to this point, there is an envelope like this, so that the extremals are going like this and touching it tangentially like this. And so this point here here, supposing that this is the extremal A star C. So, for given this is the extremal y equal to y x c, and so this A star C, which is on the extremal passing through the point A, and having an intersection, having a tangential point here on the envelope of this family. The envelope of this family is given as y equal to y x c and del y over del c x c equal to 0. So, here so it is called C discriminant curve, and the point certainly is on the C discriminant curve. Other than this, there is the envelope of this family. If it exists, then we have the situation that the extremals from this center point of the central field will be having points here, tangential points here on the extremal. So, the point on any extremal given by y x comma c is called conjugate point, which is there on the extremal as well as on the envelope. So, that is called conjugate point of A. So, the Jacobi condition is, Jacobi's condition implies that B here, this B point should be here. So, B should be on A star C 0 here. So, that is what we have for C equal to C 0, we are there on this. So, A star C 0 like this. So, that is the Jacobi condition, means that the Jacobi equation has the solution u, which vanishes only at this point, and then this point A star C 0, and therefore, it does not vanish before. So, x 2 is here. So, this here on x, so that is, let us say, x star C here, which is the abscissa of this point A star C 0. So, x 2 should be such that it should be prior to this x star C. So, that is the Jacobi condition which we had considered earlier. Then we consider the Weierstrass function, this Weierstrass function w x y y prime p, which we defined as f x y y dash minus f x y p minus y prime minus p times f p x y p. Here p is actually, p of x is dy by dx at x c 0. So, that means on the extremal we denote this y prime equal to p, which is the extremal y x c 0. So, we want to test whether this extremal satisfies certain conditions which are called sufficient condition, which will ensure the functional I to have either minimum or maximum. So, we will see that under what conditions we have the maximum value of the functional I, and under what other conditions the minimum value of the function. So, we have seen that here we considered the following situation. Here we have this extremal going like this from A, and here we have this B here, and so this is the extremal y x c 0, and we consider any other curve, admissible curve. So, we will call this y x c 0 as gamma. So, this we denote as gamma 0, and this curve gamma any admissible curve through A and B. And then we consider this I 0 of, that is y c 0, which is x 1 to x 2. So, we will write that as over gamma 0 f of x y, and here y prime is p, and I y any other curve y admissible curve like this f x y and y prime dx. Then we consider this delta I y, which is the difference of these two, gamma f of x y y dash dx minus gamma 0 f of x y p dx. Observing that we have on, if that y equal to y x c is fixed, then this I, or rather we take on this I 0 is fixed, then this I 0 y, which is this c 0, is actually a function of this x 2 y 2 moving on the extremal y equal to y x c 0. And we have seen, and we have this d of I 0 at, let us say x 2 y 2 we write as general x y moving on the extremal. Then we have seen that this is actually f minus p f p evaluated at general point x y dx plus f p dy. And so, this is, therefore, this is exact function here, that is f minus p f p dx plus f p dy is exact. Hence, the integral this over x 1 to x 2 f or on any curve gamma f minus p f p dx plus f p dy is path independent. Therefore, we have seen that this over gamma f minus p f p dx plus f p dy is same thing as gamma 0 f minus p f p dx plus f p dy, and then on this we write this as gamma 0 f minus p f p, and take this dx is taken out. So, f p and then dy by dx, which is p here, which is over gamma 0 f minus p f p plus p f p dx. So, it's cancelled. So, you get for gamma 0 f, which is x y p dx here. And so, we can therefore, we have seen that this delta I y, which is the difference between gamma f x y p y prime dx minus gamma 0 f x y p dx, and then using this previous result here, we get this as gamma f x y y dash dx minus, now we can write from here, this is the same thing as on gamma. So, on gamma 0 f x y p is same thing as this. So, let us call this as 19.1, and so using that 19.1, this integral, second integral, can be written as gamma integration over gamma f x y p minus p f x y p dx, here f minus p f p dx, f minus p f p dx, f p dx plus f p x y p dy. And so, this we would write as f x y y dash, taking dx out, and on gamma here dy by dx is y prime. So, we get this f x y p minus this y prime, minus minus will make it plus. So, minus of this f p x y p dx. So, this is what is our Weierstrass function x y y prime p dx. So, we see that this delta I y, we know that w here, this w is 0 on y x c 0, because on this y prime is p. So, you get y prime equal to p, and here also y prime is p. So, both the terms will be 0, and delta I y will be greater than equal to 0 if w is greater than equal to 0, and so we will have I y. So, that implies, so it means that I, this delta I y c 0 is 0, and in the neighborhood of this there are other extremals or any curve y, admissible curve y, which joins the points a and b. We see that delta I y is greater than 0 if w is greater than equal to 0, and so we have minimum, or let us write it, if w is greater than 0 for any value of y prime, then we get strong minimum, because here since y it does not depend on y prime. So, we have 0 order proximity, and if this delta I y will if w is greater than 0 for y prime close to p, then we get weak minimum. Similarly, if w is less than equal to 0 for any value of y prime, we have strong maximum, since in this case delta I y will be negative for arbitrary values of y prime. If w is less than equal to 0 for y prime close to p, then we get weak maximum. So, that is what we had considered last time through various examples, and so here we have to just check whether this w is positive or negative in the neighborhood of our extremal which we want to test. So, we will consider some examples here. So, let us call this 19.2 I y equal to x 1 to x 2 y prime cube dx. Here y of x 1 equal to 0, y of x 2 equal to y 2. We assume that this y 2 is greater than 0 and this x 1 is less than x 2. So, here since this f which is y prime cube is independent of x and y, the extremals are straight lines, say y equal to alpha x plus beta. Now, y at x 1 equal to 0 implies that y x equal to some constant times x minus x 1, and y at x 2 equal to y 2, which is positive. So, this will imply that C must be equal to y 2 over x 2 minus x 1, and so we get these extremals like this. So, these are depicted here. So, this is the point A which is x 1 0, and these are the straight lines. So, this extremal here, this is x 2 here, and this is x 2 y 2, and the slope of this. So, P here which is y prime on this. So, this is B here, this is B like this. So, P is y 2 over x 2 minus x 1, which is positive by our assumption that y 2 is positive and x 2 is greater than x 1. So, there are other extremals going like this in the neighborhood of this. And so, we check that w x y y prime p, which is f of x y y prime minus f of x y p minus y prime minus p f p x y p. So, this in this case will be y prime cube minus, now y prime we have to substitute p here on the extremal. So, p cube minus this y prime minus p into f p means 3 p square. So, this is equal to y prime cube minus p cube minus 3 y prime p square plus 3 p cube. So, that is equal to y prime cube minus 3 y prime p square plus 2 p cube. Here we can see that we can write it as y prime cube minus 4 y prime p square plus p square, taking common in this. So, you get y prime plus 2 p, and then here we take this as y prime, here taking y prime common. So, you get y prime equal to y prime minus y prime square minus 4 p square plus p square into y prime plus 2 p. And so, factorizing the second factor, y prime plus 2 p into y prime minus 2 p minus p square y prime plus 2 p. So, this finally gives us y prime plus 2 p into y prime minus y prime square minus 2 p y prime square minus 2 p y prime plus p square. So, that is y prime plus 2 p into y prime minus p whole square. So, you can see that since this is a non-negative, and so since p is positive here, and if y prime is close to p, then we have y prime positive. So, it is like this, you have 0 here and p is here, and supposing we take this small neighborhood around this. So, that y prime lies in this. So, then y prime will be positive here. So, we can see that is if we take, so if we take y prime lying in the interval p by 2 to 3 p by 2. So, then we see that then y prime will be positive. So, if y prime is close to p like this, so that it does not this neighborhood does not take this 0 inside, we see that y prime will be positive. And so, this w will be positive here, hence we have weak minimum. Since here the sign of W depends on y prime. So, it is actually in the first order proximity, because y prime will have to be close to p, that means derivatives will have to be derivatives of these nearby functions should be close enough. So, that is the first order proximity which was defined earlier. Now, the next example, this is 90.3 we will write. So, here I y is integral x 1 to x 2 6 y prime square minus y prime to the power 4 plus y prime dx, and the conditions are y of x 1 equal to 0 and y of x 2 equal to y 2. Again we assume that this is positive and this x 2 is greater than x 1. So, x 1 less than x 2, and so here f is 6 y prime square minus y prime power 4 plus y prime, and the extremals are solutions of this f y minus d by dx of f y prime equal to 0 implies, that is Euler's equation. So, it gives us f y gives us y prime here and minus d by dx of f y prime means 12 y prime minus 4 y prime cube plus y equal to 0. So, we get y prime minus 12 y double prime plus 12 y prime square y double prime minus y prime equal to 0. So, we get this cancels here, and so minus, sorry, this should have been f y minus 6 y prime here, this okay, y double prime. So, we take minus 12 y out, y double prime out. So, we get some sign cut this minus 12 y double prime into 1 minus y prime square equal to 0. So, this implies that either y double prime equal to 0 or y prime equal to plus minus 1, and integrating it again we get y equal to alpha x plus beta or y equal to plus minus x plus gamma. So, we get straight lines as extremals, and y at x 1 equal to 0 would imply that y of x must be some c constant times x minus x 1, and y at x 2 equal to y 2, this implies that y x equal to y 2 over x 2 minus x 1 to x minus x 1 as we had got earlier. And so, here, so on this extremal p is y 2 over x 2 minus x 1, which is positive. Now, we look at the sign of this x y y prime p, that is the Weierstrass function, which is defined as f of x y y prime minus f x y p minus y prime minus p times f p of x y p, and so it in this case we get equal to 6 y prime square minus y prime to the power 4 plus y prime, that is f here f x y prime, and then same thing at y prime replaced by p. So, we get minus 6 p square minus p to the power 4 plus y p, and then minus y prime minus p, and f differentiated partially with respect to p here when y prime is replaced by p. So, we get 12 p minus 4 p cube plus y p. So, this can be simplified finally as minus y prime minus p whole square times y prime square plus 2 p y prime minus 6 minus 3 p square. So, if we denote this expression in the bracket as E, which is function of y prime p only, and so that is y prime square plus 2 p y prime minus 6 minus 3 p square, and so we have to check this. So, if w will be positive if E is negative, and w will be negative if E is positive. So, we have to see that if E is negative, then w is positive. In this case, we will have either strong minimum or weak minimum in the first case, and in the second case we will have strong maximum or weak maximum depending upon whether it is dependent on y prime or not. So, we just check the sign of E. So, E equal to 0 implies that this y prime square plus 2 p y prime minus 6 minus 3 p square equal to 0. So, this the roots of this equation are y prime equal to minus p plus minus square root p square plus 6 minus 3 p square, that is minus p plus minus root 6 minus 2 p square. So, we check the various cases when 6 minus 2 p square is positive, when it is 0, and when it is negative. So, first case when if 6 minus 2 p square is less than 0, then we get complex roots, hence E will not vanish on this line. So, here we have like this P and this is E here. So, on the P axis here E will not vanish on the. So, there are no points here on P axis where E will be 0, will not vanish for any real P. So, we can remove this thing, not needed. So, here and this E is positive for large y prime, for any real value of not for any real value of y prime. For large y prime is is positive, because we can see that y prime is the dominating term here, and so if y prime square is the dominating term here, and if y prime is large, y prime square will decide the sign of E, and so for large values of y prime, E will be positive. Hence, if P is, that means 6 minus 2 p square negative, that is P greater than root 3 here, E will be positive for all y prime. And so, this will imply that W is negative for all y prime values of y prime. So, we get strong maximum for P greater than root 3. So, that is the first case, and when so here we see that if P is, when P is 1 and y prime is also 1, we see that E equal to 1 plus 2. So, we substitute P and y prime equal to 1 minus 6 minus 3. So, that is 0. So, and for P greater than 1 and y prime close to P we take these intervals that y prime is in P plus 1 by 2 to 3 P minus 1 by 2, then y prime will be greater than 1, and so E will be greater than 1 plus 2 minus 3, and that is equal to 0, and this will imply that W is less than 0 for P greater than 1 and y prime close to P. That means y prime also greater than 1. Thus, we have weak maximum here. Similarly, if P is less than 1 and y prime close to P, say y prime lying in the interval 3 P minus 1 by 2 to 1 plus P by 2, then y prime will be less than 1, and then E will be negative, and this implies that W is positive for these ranges of P and y prime. Thus, hence we get weak minimum. So, here we have the following picture, that we have here x 1 and then here we have x 2, and these are the extremals going here, and let us say this is the point here lying on this extremal B, which is x 2 y 2 having P equal to y 2 over x 2 minus x 1, positive, and here we see that if in this range if p is greater than 1. So, that is we have this situation that pi by 3 and then we have pi by 4. So, this corresponds to p equal to root 3, this corresponds to p equal to 1, and so here when p is greater than the slope is greater than root 3. So, here we get strong maximum, here we get weak maximum, and here we get weak minimum in this range. So, that is x and y axis here, and this is the point x 1 like this. So, in this case we have seen that the depending upon what is the slope p, and in the neighborhood of this, if y prime has close value or close to p, then we can decide that the functional whether it will have a strong maximum or weak maximum or weak minimum within those ranges of p and y prime. Next, in the next lecture we will be considering various cases of these functionals, and we will see we will get other condition which is known as Legendre condition, which is simpler to check. Here finding that w is positive or negative is difficult. If we straight away apply the definition of w, we will see that we will use the Taylor series expansion of w, and we will be able to get a nice condition easy to verify, which is known as Legendre condition. That we will consider in the next lecture. Thank you very much.